Okay, and now we can record the meeting for you after, if you need to revise or return back to it after finishing the class.
Mum, you haven't washed your smoothie thing out. You haven't? Yeah? Like, can you do it, please?
Okay, guys, can you all hear me now? Can we start, or we are only 9 now?
Yeah.
We can start. Okay, thank you. Okay, today we will continue the shear force and bending moment calculation, but today we will use the graphical method. Last week we know how to determine or calculate the shear and bending moment at some sections, but today we will use the graphical method to find the shear force diagram and bending moment diagram for the whole beam. Okay, if you remember, we have studied this beam. Okay, can you see what I shared now?
Yeah.
Okay, if you remember, we have studied this example last week, but we was only calculating the shear force and moment at B and C. Today we will use the graphical method to draw the shear force diagram and bending moment diagram for the whole beam. Okay, now I will start with you. We'll shift to another screen now. So this screen, so we will shear force diagram. This is our objective today, and bending moment diagram using graphical method. Okay, before solving this example, I will give you some cases to keep in mind before starting our tutorial today. Okay, our first case, if we have simple beam, simple beam means like beam with one support hinge and one support roller. Okay, if we have simple beam with one concentrated load B at the middle of the beam or the mid span. If the span L, so L by 2 divided by 2 and L divided by 2. Okay, this case is a concentrated force or concentrated load in the middle. Okay, if we want to draw the shear force diagram and bending moment diagram for this beam, first of all we need to find the reactions. How many reactions we have here? If this point A, this point B, so we have YA, YB, and XA. Because we don't have any horizontal forces, so XA should be 0. Okay, and as we have the force P in the middle, so should be half go to the right support and half go to the left support. So YA will be the force B divided by 2, and the other Y will be the force P divided by 2. Okay, this is our first step, is the reaction. After the reaction, we need to calculate the shear at some cuts or at some section. Where to make cut to find the shear force and bending moment diagram. So now we are going to know where to put or make our cuts or sections. Okay. First of all, our first cut is the beginning or start and end of the beam. So if we have a look here, we need to have section here, 1 at the beginning of the beam, and we will have here another section 2 at the end of the beam. Okay, we need also to have cut or section before and after concentrated loads. If we have concentrated load, so we need to have a section before and after the force. So we will have here one section here and one section here. Okay, so I will call this 2 and this 3 and this section 4. Okay, so now we know that we have 4 sections. Another case, we need to put section start and end of uniform distributed load. If we have uniform distributed load like this one, if we have something like this, uniform distributed load, so we need to have a cut at the start and a cut at the end. For this case, we don't have any uniform load, so we don't have to put cuts. Okay, the last thing, if we have concentrated moment, so we need to before and after. If we have concentrated moment, so we need to have cut before and after concentrated moment. Like this one, if we have moment like this, so we need to have one cut here and one cut here. Okay, this is where to make our cuts. So now we have 4 cuts to calculate the shear and moment diagrams. Okay, so the second step after the reaction and making our cuts, we have to, like, we will have some guidelines to put our diagram. So our cuts will be, our guidelines will be at our cuts. Here 2 and 3 at same point just after and before the force, so we have only one guide here at the mid span. Okay, so we can call this yellow lines as guide lines. Okay, the second thing after the guidelines, we will have like a datum. So this datum to put our graph or our diagram on. Okay, this datum is parallel, to the beam. So our beam is horizontal beam, so the datum is parallel to it, so it will be also horizontal. Okay, on this datum we will put our shear force diagram. Okay, so shear force diagram, we will start with it. First of all, we have datum horizontal because the beam is horizontal, and we have 3 guidelines at our 4 cuts. Okay, now we can start calculating our shear force diagram, or start drawing our shear force diagram. Okay, we'll just remove this here.
Afternoon, Ahmed.
Good afternoon. Hello, Ron. How are you?
Yeah, we're getting there, mate. We're getting
Okay. So now we are drawing the shear force diagram for this simple beam. This case is one of the basic case if we have simple beam with only one concentrated load at the midspan. Okay, so we have 4 cuts and we have guidelines and datum to draw our shear force diagram. First of all, shear force diagram at section 1. If we want to calculate or determine the shear force diagram at section 1. Where is section 1? This section 1. If we have this cut, so what is the force causing shear force at section 1? Like last week, we said last week, shear at section 1 will be, shear means the vertical force. So the shear at 1 caused by the reaction, which is B divided by 2. So the shear value at 1 will be B divided by 2. Okay, but where to put it? above the datum because we have this datum, so we have above the datum and below the datum. So where to put this value, above or below the datum? We have rule if we are calculating or drawing shear from the left. So our drawing rule, if we are from the left, if we have force going upward, so the shear will be above the datum. Okay, or in another meaning, if the force going upward, so we're going upward. If the force going downward, so we are going with the force downward. So here the shear at 1 is B divided by 2, and the force is going upward, so we are going upward like this, and the shear value will be B divided by 2. Okay, from cut 1 to cut 2. In cut 2, this will be our cut or our part we deal with. So what will be the shear again? The shear again will be divided by 2. Okay, to make it easy, we don't have to calculate each time from the beginning. From cut 1, this cut, to cut 2, do we have any forces applied between cut 1 and 2? We have no cuts.
No.
So the shear should be similar. Okay, so the shear at 2 will be similar to 1. This means that if we don't have any forces, so we will have straight line parallel to the data because no forces applied. Okay, now we can shift from 2 to 3. What happened from cut 2 to cut 3? What is the applied force?
B.
B. So B will be included in our calculation. So from 2 to 3 we have B. B is going downward or upward? Downward. So from B divided by 2 we go with a value B. So we will stop at B divided by 2.
2.
Right? Why downward? Because the force B downward. Okay. From cut 3 to 4, do we have any forces?
No.
No. So the shear should be constant, and the value here will be divided by 2. After cut 4, what we have?
B on 2.
B on 2. So from B on 2, B divided by 2, we go with B divided by 2 to 0 again. So now we should notice that we start from 0, which is the datum, and end with 0. This means this is our check for this calculation or this graph. If we reach 0 again, so this means our calculation is okay. If not, so we need to check our reaction calculation again. Okay?
Okay.
Okay. So now we know how to draw the shear. What is the sign convention for the shear? We should put like positive or negative. Above the datum is positive sign.
Positive.
Below the datum is
Negative.
so
Negative. Okay.
this will be positive and this will be negative sign. Okay, so the shear will be positive above the datum, negative below the datum. Okay,
Okay.
this is a shear force diagram. Here we said if we are working from the left, so we go with the force upward or downward. Okay, if we try to draw from the right, the opposite will be applied. Okay, that's why it's better always to work from the left in shear. Okay, the opposite mean if the force going upward, this mean our shear will be
Below.
below the datum or downward. Okay.
Yep.
Okay, I will just show you in another screen. If we try in this, just to keep in mind this, if we are in same case here, and if we try to apply this to our problem here, we now know this reaction, B divided by 2 and B divided by 2. Okay, and we have 4 cuts, 1, 2, 3, 4. Okay, and this is our datum, and this is our guidelines, and this is our data. If we want to draw the shear force diagram for this beam from the right, what causing shear here? For section 4,
Yeah.
B divided by 2. Okay, but going upward, if we do the same from left, so the shear will be something like this, right? So the shear will be something like this. Is that right? Is that the same shear we have in the last calculation we have?
Yeah.
No,
Mm.
this is the opposite. The correct answer is like this, right? But now it is not right because we consider same rule from the right. But again, from the right, if the force going upward, this means that shear below. We will not use this rule, but I just try to explain that both method. If you if you use the same procedure in both direction, this will be wrong. So you need to be careful. Okay. So here we don't have to use the shear from right. I will only make shear from left, so you are not confused now. Okay. So shear from left, we go upward with the force or downward with the force. Okay. Now we can shift to the moment. For the moment, we have same cuts as last cuts in the shear. Okay. So now we have section 1, section 2, section 3, section 4. Okay. And we will have, this is our datum. And we need to draw the bending moment diagram for this beam. How to draw the bending moment diagram for this beam? We will start the same as we start in shear. We will start with section 1 or cut 1. What cause moment at section 1? If this section 1, is there any force causing moment, or is there any moment at 1? What cause moment at 1? This force is the only force we have, and this force passing through 1, so the moment should be 0. If the force passing through, so the moment is 0. So the
Yeah,
moment
0.
should be 0 because no moment at the beginning of the beam. Okay. At section 2, if we take this cut 2, what causing moment at 2?
The upward force on the left-hand side there at point
Yeah.
1.
So M2, if we try to calculate it here, we have only this force causing moment at section 2, right? So the
Yep.
moment will be B divided by 2 multiplied by the distance. What is the distance? L
2.
divided by 2. So the moment will be BL divided by 4. Okay. So the value of the moment here at this section is BL divided by 4. Okay. Where to put this moment? Above the datum or below the datum? Again, we have here above the datum and below the datum. Okay.
Up.
Okay. Up or down?
Up.
Below.
Below.
Okay. Okay. I will tell you why below. If we are here, this is section 2. Okay. This is our cut. Do we have any other forces here?
Oh, I see. It's a
We have
reaction.
only
Yep.
this force. Okay. And you are here. Okay. So what is the moment caused by this force? What is the direction? This is the moment. Okay.
Yep.
Sorry.
PL over 4.
Okay. Okay. This is the force and this is the distance. Okay. And we know now the value is BL divided by 4. Okay. We put the moment with the tail of the force or the tail of the moment. Okay. So the tail of the moment, if we have like arrow like this, we have tail and head. Okay. So where to put the moment? With the tail, because the tail means the positive or the tension, because you know that any moment cause tension inside and compression in another side, right?
Mhm.
So that's why we put the moment with the tail. This means we put the moment with the tension side. So here for this force, what is the direction of the tail? Downward or upward or below or above the
Below.
data? Below. So the moment, the resulting moment should be below as well. That's why we will put it here. The moment here will be BL divided by 4. Okay? From section 1 or cut 1 and cut 2. Do we have any uniform loads? Or do you have any loads? We don't have any loads here. So we connect the moment at 1 with the connect at 2 with a straight line.
Okay.
So the moment here, because we don't have any forces, straight line. So again, in the moment, we calculate at section 1 and then calculate at section 2, then connect between them with a straight line. Is that okay? Okay. From 2 to 3, do we have to calculate the moment at 3? We know that the moment at 2 is BL divided by 4. The moment at 3, from last week, we said that the moment from the right and from the left should be similar at any point, right? Do you remember
Yes.
this?
Yep.
So we don't have to calculate the moment at 3, okay? Because M3 equal to M2. Okay, now we go to M4. What is the moment at 4? Do you have any idea? If we apply, yeah.
P times L over P.
No, we don't have to calculate from the left, because if we calculate from the left here,
It's 0.
yeah, this will be like not unlogic, because we have 1, 2 forces, and here if we apply from here, very easy and simple, and because we have only one force. So always we need to like simplify our calculation to be easy. Okay, so at 4, it's better to calculate from the left. From the left, the moment should be 0. Why should be 0? Because this force passing through the cut, so no moment for it. Okay, so the moment at 4 is 0. How to connect between 3 and 4? How to connect between this point and this point?
Could be a straight line.
Straight line as well, because we don't have any forces. Okay, so this is how to deal with the moment. We calculate at our section or our cuts we defined before, then connect these values with straight line, because we don't have any forces, okay, between them. Okay, what is the sign convention for the moment?
Clockwise is negative and counterclockwise is positive.
But this is
Oh, below the line. Below
yeah,
the line is
we have,
negative.
yeah, we have above and below now. Okay.
Yep.
Okay. Now, if they are, there is agreement between all people or all engineers that above the datum is negative, below the datum is positive. Okay. This means that our moments here will be positive. Why positive again? If you return back to this rule, as I said before, the moment has tail and head. The tail causing tension. Tension is positive. The head is compression, and the compression is negative. That's why if you put the moment underneath the datum, this means that this side is under tension, not under compression. Okay?
Yep.
Do you have any problem in the moment and shear for simple beam with concentrated load?
No.
Okay, that's good. So now we can shift to the second case. If we have the same simple beam but with uniform distributed load, we can call it W. Okay, if we have uniform load W and a span of the beam L, and one of them is hinge and one of them is roller, okay, we can call this case is the uniform distributed load. Okay, first of all, before calculating the moment and the reaction, the moment and shear diagrams, we need to find the reaction. How many reactions do we have? 3. If this A and this B, so we have YA, YB, and XA. XA should be, XB, sorry, should be
0.
because we don't have any forces in X direction. How to find YA and YB? Before finding YA and YB, how can we deal with the uniform load? We need to concentrate the uniform load in one equivalent consultant. What is the value of this consultant? W multiplied by L, right?
Yeah.
W is the load, L is the span. So now what is the reaction here and what is the reaction here with the same concept of the last example?
W1 and 2.
Yeah, if we have one load in the middle and the beam is like symmetric, so half of the load should be here, WL by 2, and half WL by 2. Okay. So I will just check the shear. Okay. Do you have any problem with calculating these reactions?
No.
Because it's very simple, so you don't have to use the calculation equation or equilibrium equation. Okay. Now our turn to the cuts. How many cuts we have in this beam? We just say the rule in the previous example. How many cuts do you think? 3 or
3.
4, 2 or 3 or 4?
3.
We start one at the start and what at the end. Okay. Do we need more? We said one at the beginning and one at the end. One and
One
after.
after.
Yeah, and before and after concentrated load. Do we have any concentrated load here?
No.
No. So we don't need to. This is not concentrated load, right?
No.
This is only equivalent force for the uniform load. So we have only 2 cuts, one at the start and end of the beam, and also one and start of the uniform load. So we have only 2. Okay. So we will have one here and one here guideline. Okay. So now we can put our datum. This will be our datum to draw the shear force diagram. Okay. If we start with cut 1, if this is our cut 1, what causing shear at 1? The reaction, or do we have any other thing causing shear? Only this force causing shear. So our
Yeah.
shear and the force is going upward, right? So if the force going upward, this means that we have shear here. The value is WL divided by 2.
2.
Okay. From 1 to 2. This cut 1 and this cut 2. What is the forces we have? What is the applied force from 1 to 2? This force, right?
Yeah.
How can we deal with the uniform load? Because the uniform load is different from the concentrated load. So what we will do is we calculate the shear at the start, and the shear at the end will be the shear at the start, which is WL by 2, minus the equivalent resultant, which is WL. Okay, this gives us negative WL by 2. Okay, this is how we deal with. Sorry guys, can you mute him? Okay, so the shear at the end, this is the end of the uniform load, this is the start of the uniform load. The shear at the end will be the shear at the start minus the equivalent uniform load. Okay.
Yeah.
Okay, so the shear value will be minus WL by 2. What this negative sign mean? Below or above the datum?
Below.
Below. Okay, so this means that the shear here is also WL by 2. Okay. This means that the shear here is WL by 2. Okay. Do you have any problem in this one? So we need to calculate at the start WL by 2 here. Then to calculate at the end the shear at the start minus the force. Okay. And how to connect between these two values? We connect between these two values with a straight line. Okay. So again, we know the shear at the start, WL by 2. And here the shear will be WL by 2 minus WL give us WL by 2 below the data. And we connect them with a straight line. Okay. After section 2, what we have after section 2? We have this shear or this force WL by 2. This force will make us reach the 0 again. So we start with 0 and end with 0. Okay. What is the sign for this shear? Here above the datum positive, here below the datum so negative. Okay. Do you have any question about this one?
No.
Okay. So now we can shift to the moment. For same case, if we have the simple beam with a uniform load W, and we have this L is we say that we have uniform equivalent resultant WL, and the reaction here WL by 2, the reaction here WL by 2, and we have two cuts, 1 and 2. Okay, so we have this guideline, and we will have datum to calculate the bending moment diagram. Okay, now we can calculate the moment. What is the moment at 1? What causing moment at 1?
0.
0, because the force WL passing through, so the moment at 1 should be 0. What is the moment at 2? If we calculate from the right, the moment at 2 also will be 0.
Yeah.
So if we have uniform load, the moment at the start will be 0, the moment at the end will be 0. How to connect between these 2 points? The moment for this case, the maximum moment will be at the middle. So this is the maximum moment. M maximum will be WL square divided by 8. Okay. This is our maximum bending moment. Where is this moment? Below the datum, and what is the value? WL square by 8. How to connect these three values? 0 here, 0 here, and WL square by 8. By straight line, or we should have another way to connect? Because a straight line, if we don't have forces or we don't have any uniform loads, so here we will connect with a curve or a parabola. So the moment here will be second degree parabola. Okay, so this is the moment for the uniform load. If we have uniform load again, the moment at the start 0, the moment at the end 0, maximum moment at the middle or at mid span is WL square by 8, and we connect with a second degree parabola. Okay, what is the sign convention for this moment, positive or negative? Again, we said below the datum is positive, above the datum is negative. So this moment is positive moment. Okay, so again, the moment, if we have uniform distributed load, the value will be WL squared divided by 8 and second degree parabola. Okay. Okay, so do you have any question regarding this case? If we make a summary to compare, if we have concentrated load B, because you should keep this in mind. And if we have uniform load W, the shear for this one, we will have this data. The shear for this one, this will be the shear. The shear will be, if this direction, B by 2, and here the direction B divided by 2. So this is our shear, B divided by 2, and here B by 2, and here B by 2, and here B by 2, and here. This will be positive, this will be negative. For the moment, the bending moment diagram. For the moment, what is the moment here? We said before the moment here 0, the moment here 0, the maximum moment here BL divided by 4, and we connect it with a straight line. And the sign convention here is positive. Okay, if we make a comparison here, so what is that we said before here, the shear value, the resultant value WL, the reaction here WL by 2, the reaction here WL by 2. Okay, for the shear force diagram, we said the shear at the start or at the beginning of the beam WL by 2, the shear at the end will be WL by 2 minus WL, give us WL by 2. Okay, and we connect it with a straight line. Then after this, the reaction return back to 0. The sign convention here positive, here negative. Okay, for the bending moment diagram, the moment at the start 0, the moment at the end 0, the maximum moment is here at the middle, WL square by 8, and we connect this with a second degree parabola. Okay, and the sign convention will be positive. Okay,
Yeah.
what do you notice between, if we compare between these two cases? Here, if you consider the shear in the case of concentrated load is constant. Constant mean it is parallel to the datum because no forces. Here, the shear is linear, has linear variation on with the length. Okay, so you have to consider this in your mind. Okay, for the moment, if we have concentrated force, so the moment is line. If we have uniform load, so the moment should be parabola or curve. Okay, these two cases is very important for you to keep in mind because this is our basic in drawing moment and shear. Okay, and I will upload this slides for you if you need it, this answer to Ron. And I also today I'm recording the session so I can upload as well.
Thank you.
If you need it, no worries. Okay, so this is our cases we have done till now. Now we can shift to our class example. Okay, this one. This is our class example now. Do you want to try it first? Okay, I will give you 5 minutes to try this one. Are you happy with this, or I start with this one and keep the second one for you?
Could you do this one first, and then we can do the
Okay.
next one?
Okay. Okay. So to make it, I will do the harder one and I keep this one for you. Okay. So we can save some time. I will do the tutorial question. Okay. Do you remember this question? We have tried this question last week, if you remember.
Yep.
Okay. But last week, the requirement was only bending moment at C and shear force and moment at C and D. But today, we will try to draw the shear force diagram and bending moment diagram for the whole beam. Okay? And I will start with this one. So, okay. For this one, so we have simple beam. One support hinge, one support roller, A, B. We have force here at C, 800 Newton. Here at D, 1500 Newton. This distance, 125, 600 millimeter, and 75 millimeter. Okay. To make it easy for the moment calculation, I will convert this to meter. Okay. So 0.6 meter, 0.075 meter. Okay. The requirement is to draw shear force diagram and bending moment diagram. Diagram means you should use the graphical method. No option to use the analytical method or the method we used last week. Okay? Because it's diagram. So now we need to start the start to solve this problem. How can we start? First of all, we need to know that we have here two reaction, XA, YA, and YB. Okay? So we have XA and YA and YB. Okay? XA should be 0 because we don't have any horizontal force. So reactions, we have done this reaction last week, but I will revise with you. If we want to find the reaction YA and YB, to find YB, we will take the moment at A. So summation moment at A should be 0. What causing moment at A? YB multiplied by the distance, which is 800 millimeter. Okay. Positive because it rotates in this direction. This force minus 1500 multiplied by 600 because it is clockwise. This force also clockwise. So
Shouldn't that be 725?
yeah, sorry. Thanks, Ron.
Yeah, I thought I was wrong once, but I was mistaken.
Thank you. So 725 because we are the distance here. 725. The distance here 800. The distance here is 125. Okay. So the last force 800 by 125. All of this should be 0. So YB will be positive 1484.625. Okay, Newton. How to find YA? If we apply summation if Y equal to 0, so YA plus YB 1484 minus this force because downward should be 0. So YA will be 815.375 Newton. Okay, so these two reaction we have. So now we will simplify this here. We have 800, 1500, and this is our distance. The reaction here, 815. The reaction here, 1484, 625. Okay. How to draw the shear force diagram? We said before we need to determine or assign our cuts. So we have 1, 2, 3, 4, 5, 6 cuts. Are you agree with this cuts or we need more cuts?
No, that's
Start,
sufficient.
start and end of the beam before and after each concentrated load. Okay, so we don't need more. So this is our guidelines. We'll have 4 guidelines here, and now we have this our datum, and this will be our shear force diagram. Okay. If we start at section 1, what causes shear at section 1?
815.
A15, yeah.
Okay, so we'll have upward or downward? The force
Upward.
upward, so this 815 upward. Okay. From 1 to 2, do we have any
No
forces?
change.
No
No
change.
change.
So constant. From 2 to 3, we have this
800 down.
so 800 down. So
We end up at 15.375.
yeah, 15.375. Okay. Do you have any comment? Because we have force, so we have a drop. From 3 to 4, we don't have any forces, so should be constant.
Hold on.
50.
Same.
Okay. Then from 4 to 5, what we have? This force. So should
100 down.
1500 down, yep.
so we'll go to
1484.
yeah 0.625. From 5 to 6, we have no
No
change,
change.
so constant. Then we have
A horizontal up. A vertical up.
yeah vertical up because we start from 0, so should end
We
at
finish at 0. And we do.
yeah. So our calculation is okay, no problem with the reaction. What is the sign for this diagram? Above the datum is positive, below the datum is
Minus.
Negative.
okay. Easy. Do you have any comment or any question for this problem?
No.
Shear force is pretty straightforward.
Yeah. Okay. So now we can go to the moment. Okay. So for the moment calculation, bending moment diagram. What is the moment at the beginning of the beam? What is the moment at 1? At 1,
0.
only this force causing moment at the passing through, so the moment should be 0 at 1. Okay. What is the moment at 2? If you are at 2, I will put the calculation here. If you need to make calculation, so you can do calculation. You don't have to only draw the graph, or you can have some calculation. Okay, if you need. So if we are at section 2, what causing moment at 2?
Vertical force.
This force causing moment, right?
Yep.
So M at 2 will be 815.375 multiplied by the distance. What is the distance?
125 millimeters.
Yeah, this distance, which is 0.125 meter or 125 meter. Okay, this gives us the moment here will be 101.9 Newton meter. Okay. The second problem now, we now know the value, but where to put it? Above the datum or below the datum? What do you think?
Below.
Above. Sorry, no, below.
Below.
Again,
below.
wait, this is our force causing the
Yeah.
moment, right?
Tail is below,
So
so
the
it's
tail is below.
Yep.
So the moment here will be below 100.9 Newton meter. How to connect between 1 and 2?
Straight line.
Straight line. Sorry for this straight line. Okay. And try to make it better. Okay. So we have a straight line here. Okay. Now do we need to calculate at 3? M at 3 should be M at 2.
Two.
Right? M now go to M4. M4 we can calculate from here or calculate from here. What do you think is better for this one?
From the right.
From the right, because we have only one force. So if we calculate M4 from the right, what cause moment at 4 from the right?
1484.625.
Yeah, 1484.625 multiplied by the distance. What is
0.075.
0.7.
Yeah, 0.075. So this gives us the moment 1100.3 Newton meter. So the moment here is 111.3. Where to put this moment, above the datum or below the datum?
Below.
Again, if you see here, this is the rotation of this moment. So the tail is under the datum. This means the moment should be above or below the datum? Below. And this one is 111.3. Okay. How to connect between 3 and 4? Straight line or parabola?
Straight.
Straight line.
Yeah.
The last one, the moment at 6. Is there any moment at 6?
No.
No.
The moment at 6 should be 0 because it is the start or the end of the beam, so no moment. How to connect between 5 and 6? This area?
Straight line.
Straight line. Okay. Is that easy?
Yeah.
Okay.
Yeah.
What is the shear? What is the moment sign here? Positive?
Positive.
Below the datum. Okay. Is that okay? Do you have any
Yeah.
problem with this beam?
Bravissimo.
Okay. Now I give you 5 minutes to practice this one, as we mentioned.
I'm getting up.
Okay. This is much easier than this one, that's the one I have calculated. But I will give you some time to practice. Okay?
Yep.
Okay. I'll give you 5 minutes or whatever you need, from 5 to 10 minutes. Okay, guys, have you tried? Have you finished it?
Mm-hmm.
Easy?
Yeah.
Okay, I will share with you the answer for your record. This is the answer you had, or you have
Yeah.
different answer?
Yeah. I've got the same answer.
Okay. All good with you in this type of problems? Okay, good. So now we'll shift to another type of problem. Okay. If you have a look on this, yeah, I'm hearing you, Ron.
Why was that one on that the moment diagram? Why was it 1 kilonewton meters, not half?
Okay, maybe, yeah, half, sorry. You're right. Yeah, one kilonewton by 0.5, so the moment will be 0.5 kilonewton meter. Okay, I will edit it now. Okay, are you happy now?
Can't see it at the moment. Don't have it open.
Okay.
Okay, next one.
Okay. So now, sorry, I was sharing the other screen, but sorry, I have already modified it. So now the second type of problem we have is the cantilever. If you remember last week, we had cantilever means beam fixed at one point, at this point fixed, and free at the other point. Okay. If we have cantilever like this, we should have some basics to know, like what we have in the simple beam. Okay. So number 3, if we have cantilever with concentrated load, this is our cantilever, fixed, free, and we have one load B at the end, and this is our span L. How can we find, or how can we draw the moment and shear diagram for this beam? First of all, if this point A and this B, how many reactions we have here? 3, XA, YA, and MA, right? XA should be 0 because no horizontal forces. YA, we have only, if we have summation Y equation, we have only one force. So YA should be equal to B. So YA will be equal to B. For MA, if we take the moment at A equal to 0, what is the moment at A? What cause moment at A if we are here at A? What causing moment here? This force and MA, right? So if we have MA rotating in anti-clockwise, so positive, minus B multiplied by L, negative because it's clockwise. So the moment at A should be BL. Okay, so MA will be B multiplied by L. Do you have any problem with this one? So if we have cantilever, we have B, the reactions B and 0, and BL is the moment. Okay. Okay, now if you want to draw the shear and moment, we need to define the cut, or our cuts or our section. How many cuts we need here? We'll have one at the start and one at the end of the beam. Do we have more? Do we need more?
No.
Because here, if we take after the beam, after the concentrated load, this cut is out of the beam, so has no meaning. So for this one, we have only 2 cuts, and we will have this our guideline here, this our guideline here. Okay, and if we put this our datum. So if this our datum, what is the shear force diagram here? With the same procedure we know, what cause shear at 1? The reaction force B, upward or downward?
Upward.
So upward here. So we have B. From 1 to 2, we don't have any forces. So the shear should be
Straight.
constant, B, right? From after 2, we have this force downward, so go to 0. The shear above the datum is positive. Okay, so again, we start from 0. We have B upward. Then from 1 to 2, we don't have any forces, so straight. From after 2, we have a force dropping down to 0 again. So this is our shear force diagram. For our bending moment diagram, how can we draw the bending moment diagram here? At 1, just cut 1. If you are at 1 here, what causing moment at 1? This force causing moment? No, because it's passing through. But this moment will cause moment at 1, right?
Yeah.
So this moment above the datum, the tail above the datum or below the datum?
Below.
The tail. Here, I will draw it here again. This one, we are here at 1. And
Above. Yep.
above the datum.
Above.
So our moment will be here above the datum, and the value is B multiplied by L.
L.
Okay, the moment at 2. We can calculate from the left or from the right. It is better or easier to do from the right. What causing moment at 2 from the right?
Nothing.
Nothing. So the moment should be
0.
from 1 to 2. We don't have any forces. So the moment we connect with a straight line
Straight
or
line.
curve.
Straight line.
Straight line. So this is our moment. This is a straight line. The moment is negative or positive here?
Negative.
Negative.
Above the datum negative, below the datum is positive. Okay, so this case is for concentrated load on a cantilever. It's okay?
Yeah.
Okay.
Yep.
Now we can shift to the case of cantilever number 4 with uniform distributed load. If we have cantilever with a uniform load W. Okay, and this span is L. How many reaction we have again here? XA,
YA, YB.
YA, and MA. This fixed support. We don't have any support here. Okay, so YA, MA, and XA. Okay, how can we find this reaction? Before we find the reaction, we need to first concentrate this uniform load WL, right? So if we apply summation Fy equal to 0, so YA should be equal to WL, right?
Mm-hmm.
So this will be WL. If we apply summation moment at A equal to 0, what causing moment at, if we are at A here, this A, what causing moment at A?
YA times WL.
Yeah, I will start with MA, positive because it's rotating anti-clockwise. This force doesn't have moment, minus this force is rotating in this direction, so negative WL multiplied by the distance. Where this force applied?
Halfway. Along
Halfway,
now.
so
So L over 2.
multiplied by L over 2, negative because it is clockwise. This should be 0. So MA will be WL square divided by 2. So the moment value here is WL square divided by 2. If you remember, in the simple beam was WL square divided by 8. Should keep this value in mind, okay? So now we know for this beam or for this cantilever, we know the shear here or the reaction here, WL, here x equal to 0, m equal to WL square divided by 2, and we have a uniform load W
Mm-hmm.
over span L.
L.
Okay. How many cuts we need for this beam? 2 or 3 or 4? If we one here at the start, one at the end. Do we need more? We don't need more because here is the start or end of the load and start or end of the beam. So they are matching together. Okay, our coincidence. Okay, so we have two cuts only. We have two guidelines. This one, and we will have this our datum. Okay, so how to draw the shear force diagram here? If we start with cut 1, what caused shear at 1?
WL.
The reaction WL,
Yeah.
right?
Yep.
So
Upwards.
upwards WL. Okay. How can we deal with the uniform load in shear? What we said before. We said before, if we have uniform load, we concentrated like here, WL. So Q1, we know Q1, WL, right? Q2 is the end of the uniform load, will be WL minus the equivalent force of the uniform load, right? So WL minus WL, this gives us the shear equal to,
0.
because we are here WL and we have WL. So WL minus WL give us the shear here equal to 0. How to connect between these two values?
Straight line.
We said before, if we have uniform load, so the shear will be a straight line. So this straight line. Okay. What is the sign convention for this one?
Plus, positive.
Positive.
Positive, because it's shear, above positive, below negative. Okay. Okay. So now we can go to shift to the moment. This is our data for the moment. So we have bending moment diagram. How can we draw the bending moment diagram for this one? If we start at cut 1, what causes moment at cut 1?
WO square on 2.
Yeah, this force passing through, so no moment for it, but this moment will cause moment at 1, right? We put it above the datum or below the datum? Again, we have a look. We should have a look on the
Tail. The
tail.
tail's above it,
The
so
tail
it
here
goes
is
above.
above, so the moment should be
Above.
above. This moment will be WL square divided by 2. The moment at 2, how much is the moment at 2? If we calculate from the right side, is there anything causing moment?
No.
No. So the moment here will be 0. How can we connect parabola or a straight line?
Parabola.
Parabola.
So to show that this is a parabola, so I will connect these two points with a straight line, then hanging the parabola. Okay. So
How do you know which way parabola goes?
you mean above or below?
Yeah. The line. That dotted orange line.
You mean this line?
Yeah, how do you know whether that is
Not like this, right?
convex or concave? Yeah.
Yeah. What do you think? Because it is second degree, so should be like this.
Concave.
Oh, right. So it should be tangent at the far end with a load 0.
Yeah. And another thing, because our force is like this, okay? So the parabola should be like this, or if it's cantilever, should be like this, because the load is downward. If the load is upward, what do you think the parabola will be?
Yep, I got you. That
Convex.
makes sense. Yep.
Okay, so the parabola direction is depending on the direction of the load. If the load downward, so the parabola will be downward. If the load upward, so the parabola will be upward. Okay, and in some cases in structural engineering, we have some upward loads like uplift pressure of water or something like this, or soil reaction of soil. if you are dealing with civil topics. Okay. Okay, I will remove this one or keep this one here. So the value here is WL squared divided by 2, and here is 0, and here is second degree parabola. Okay. Do you have any question for this moment? Michael, you are asking for this again? Okay, I will repeat this one again. Okay, I will clarify it again quickly. For the direction of the parabola, this parabola is causing from this moment, this forces, uniform load. So if the uniform load like acting downward, so the parabola will be in this direction. Okay. If the force or the uniform load acting upward, this will give us that the force, the moment will be something like this. Okay, so this case 1 and this case 2. But for our scope of study, all the moment or all the forces will be acting, this case acting downward, so this will be our moment. Okay, so now we return back to our beam. What is the sign convention for this one? Positive or negative? Again, we said negative moment above the data, positive moment below the data. So the moment will be negative. Okay. Do you have any question? So
Yeah.
now we have these two cases for cantilever, and you need to keep in mind with the two cases of simple beam. Okay. Okay. Now we will shift to the beam, the beam or the tutorial example. I think this is an example, but it's very easy. Do you have any comment on this one? What this case like? We have done it just now. Do you have comment on this one?
Uniform.
Yeah, the same as the uniform we did just now. So the very simple one. So we don't need to waste time in it. Okay. Yeah, it has like some typo here. So kilonewton rather than kilo km. There is no unit in m. So it is no Newton, not Newton, not m. Okay.
Yeah.
Okay. So I will now solve another example for you. If you have a look on this one, we have tried this last week as well, if you remember. But the requirement was only to find the moment and shear at A, and we extend to find the moment and shear at B. Okay. But today we will do it with using the graphical method to draw the shear force diagram and bending moment diagram. Okay. So I will shift now to the other screen so we can solve it together. Okay, now we have like cantilever beam, this point A, this point B, this point C. Here we have B at B, 10 kilonewton. Here we have 8 kilonewton, and we have a concentrated moment 40 kilonewton meter. We have here a uniform distributed load 2 kilonewton per meter. Okay, and the requirement to draw the shear force diagram and bending moment diagram. Okay, how can we draw the shear force diagram and bending moment diagram for this one? First of all, we need to,
Reactions.
yeah, we have 3 reactions. Okay, and we need also to concentrate this uniform load here. If this distance is 6 meter and this 4 meter, so how much the load? 2 by 6 will be
12.
12. 2 multiplied by 6, so 12. Okay,
10.
okay, and where this force applied? At distance 3 from this one and 3 from the other side. Okay, how many cuts we need in this beam? 1 at the start,
4.
1 before and after the concentrated load, 1 at the end. Okay, so 4 is enough for this one. Okay, and yeah, this the graphic for Ron, the graphical method is much preferred because you can find the moment and shear at any section with this method rather than calculating at each method. So if you draw it, so at any point you can find the moment and shear. Okay, the last tutorial was only like basics for this one, to know how to calculate and then how to draw. Okay, now we can proceed in this problem. So if we have 4 cuts, we have this guideline, and this guideline. Okay, I will make the calculation here. The first calculation is the reaction summation XA equal to 0, so XA should be 0. Summation YA equal to 0. How many forces in Y direction? 8, 10, 12, and YA. So YA minus 12 minus 10 minus 8 equal to 0. This gives us YA equal to 30 kilonewton. Okay.
Yeah.
To find MA, we need to apply the moment at A, the moment equation at A. If we at A, what causing moment at A? This force doesn't have moment. The moment has moment. This force has moment. This force has moment. This force has moment. This moment cause moment. Okay. So if we apply this equation, we will have MA anti-clockwise minus 12 multiplied by 3 clockwise minus 10 multiplied by 6 clockwise minus 8 multiplied by 10 clockwise minus 40 multiplied by 10 clockwise. Is that right?
Mm-hmm.
It has some small mistake. What is it? I just write it to maybe you can notice this one. This is a moment, right? We said
Yeah.
before that the moment already multiplied force multiplied by distance. So the moment doesn't multiply by distance here. This is a mistake and will affect your
Ah,
result, right?
yeah.
I just
24
put it
for the moment.
because this sometimes confuse you. So you have to be careful when you are dealing with moment. Moment are not multiplying but by distance again. Okay.
Yeah.
Okay. So now we find that MA will be 216 kilonewton meter. Okay. So now we know if we remove this, we put the values. Okay, so we know that this moment is 216 kilonewton meter. This reaction is 30 kilonewton. This reaction is 0. Okay, so now we can start drawing the shear force diagram. So if this is our data, can put the shear force diagram here. If we start with section 1, what causing shear at 1? If we are at 1 here, what causing shear at 1? The reaction force 30, right?
Mm-hmm.
And upward, so we go upward 30 kilonewton. Okay. From 1 to 2, what we have from 1 to 2? 12. This force 12.
Yeah.
So 30 minus 12. Upward or downward? Upward or downward?
Downward
Okay. So
to 18.
So Q2 will be 30 minus 12 should be 18. 18 above the datum or below the datum?
Above.
Above, because still positive. So
Yep.
here will be 18 kilonewton above the datum. And we connect it with a straight line because we have uniform load. Okay.
Yep.
From 2 to 3, what we have from 2 to 3?
No change.
We have this force.
Right? Minus 10.
Yeah, minus 10. We have minus 10. So from 18 to 8. Right? Because we have this force. This force applied from 2 to 3. Okay? From 3 to 4, do we have any forces?
No.
No, so
At 4, we have a negative 8.
8 kilonewton. At the end, after section 4, we have 8, so 8 just returning back to 0. So the shear sign will be positive or negative. We said above the datum positive, below the datum is
Negative.
negative. Okay? So this is the shear for this cantilever. Now we can go to the moment.
Any moment.
For the bending moment diagram, this is our datum. If we start with section 1, what is the moment at 1?
216 kilonewton meters.
Put this one here, this one. We have XA0, YA 30, and this moment 216. So
It's at 216.
yeah, we don't, this force doesn't have moment, so 0. So we have only this moment. This moment 216. So we put the value above the datum or below the datum?
Above.
Above, because the tail is above.
Above.
So the moment here is
216.
216 kilonewton meter. Okay. At section 2. So if we are here, this section 2, and we have this force 12 kilonewton. If we are at 2, this force will have moment now because it has distance. So this force 30 kilonewton. This distance is 6 meter. This distance is 3 meter. So if we calculating the moment at 2 now, M2, what causing moment at 2? This force.
Yep.
One.
Yeah.
And the
This force.
30 kilonewtons there.
Yeah. And this
Yeah.
moment.
And that
186.
All this has moment, right?
Yeah.
So how can we deal with this one?
Sum them all up.
Yeah, sum them all up. Okay. So we have 216. Okay.
Yep.
With no distance
Negative.
because it's already a moment. Negative. Why negative?
It's
Because
counter. It's clockwise. It's counterclockwise. It should be positive. My apologies.
but we said here we don't have same rule of the
Yep.
yeah, because we have above and below the datum. So if the
Right.
tail above,
Yep.
this means it is negative, right? So this above or below?
It's above, so it's negative.
So negative. Okay. Also 12 minus or positive 12 also above. So
Above, so
minus
it's
12.
negative.
multiplied by 3. Okay, plus 30 multiplied by 6. Why 30 multiplied by 6? Because if we have a look on 30, the tail is here. So we have three forces: this force, this force, this force. This force and this force, the tail is above, so negative, negative. Here, the tail is below, so positive. Okay, this is the meaning of this signs. Is that okay with you?
Yep, makes sense to me.
Okay, so if anybody has question, you can ask me or let me know. If you don't accept this,
Minus 72.
okay. So m at 2 will be minus 72 kilonewton meter. Okay. What does this minus mean?
Minus 1268.
Minus
Over.
means above or below the datum?
Above.
Above. This means that the moment here is 72 and still above the datum. Because if this was positive, where we put the moment?
Below the datum.
Below. Okay. That's why we use this rule to calculate the moment at 2. Because the result will give us how to put it or where to put it, above or below the data. Okay.
Yep.
From section 1 to 2, from 216 to 72, how can we connect these 2 points? With
Parabola
yeah, with parabola. So we will have,
and hollow down. Yeah.
yeah, I will put this just guideline to convince the marker that you are doing a parabola. Okay. Okay. Is that okay with you now?
Yeah.
Okay. So now we can calculate at 4. M at 4, how can we calculate the moment at 4? Do you have idea how much is the moment at 4?
Yeah, it's 40 kilonewton meters.
Yeah.
Minus, it's 40 kilonewton meters above.
Okay.
Using
If we have,
you go to the right and just use C. That's all you need.
yeah, if we are at 4, you are right, Ron. We are dealing with this part, right? What cause moment at 4? Is this force has moment? No, because it's force passing through, so no moment. So the only thing I have moment here
It's
has
40.
moment is 40. The tail of this force is above or below the datum? Above. So should be the moment should be above or below the datum?
Above.
Above. So the moment here will be 40 kilonewton meter above. How to connect from 72 to 40?
Straight line.
Do we have any moments? Any uniform load?
No.
No. So we connect it with
No.
a
Straight
straight
line.
line. Okay. So now we have, if you notice, for this part or this area, we have uniform distributed load, so parabola. Here we don't have any uniform load, so straight line. What is the sign convention for this drawing?
Negative.
Negative.
Negative, because above the data. Okay.
Okay. Wrap my head around that.
Okay. Are you happy with this problems? Are you happy
Yeah.
with this tutorial?
Yeah.
Okay, that's good. So these are the main cases we have: cantilever and simple beam. And I will put this. If you need this slide, I will send them to you. Do you need them? Because some of you sent me that you need it. So I will upload to you. And do you need the video?
Can you just upload them to the Learn Online?
I will try, but I haven't uploaded anything before, so I don't know. Maybe Zing doesn't accept. I don't know. I will ask him. But if so, I can send to you by email. Is that okay? I will send them to.
I'm good with that.
Okay. So Cody asking for them, so I will put them Cody. How are you, Cody? Cody wasn't here last week. Okay, do you need the video as well, or you don't need the video?
Might be good to have the video.
I don't think it won't hurt.
Okay. Okay. Okay.
It's always a
So
future reference, you know.
yeah. Okay. I already shifted to this meeting because I don't know why I'm not the host in the other meeting, but now I am the host, so I can record. Last time I couldn't record because I'm not the host. Okay. So this is the last tutorial question we have today. I will leave this to you to complete at home as exercise. And if you have any question regarding this one, you can send me. And I will send you the answer of it as well if you need.
No worries.
Okay, guys.
Thanks,
So,
mate.
all happy today? Thank you.
Thank you.
Quick word, Ahmed. Private. Hang on.
Thank you, Ron. Okay, guys. And you have, I think last week, next week is due date for the project, you know?
Yeah. Is it
Okay.
due on the Monday?
Yeah, Monday.
Okay, no worries.
Yeah. But I think if you need extension, I think no problem, but I think it's better to finish at time.
No worries
But I
then.
think Zing will not mind to give you more time if you need.
No worries.
Okay, guys.
Okay, thank you.
Have a good day. Yeah.
Bye.
See you. See you. Bye.